Well, thank you all for sticking around into the depths of the weekend and spring break. Let's see. Odds and ends. One is I put up problem set 4 on Colab this time because I wanted to be able to do it, write it myself. Hopefully you'll find it a more valuable experience. If you have trouble with it, since I have never done this before, let me know. I hope I've done it correctly. Any other questions or issues on your mind at the moment? Okay. Well, the topic at hand is rockets, and I showed you how rockets work. So now I want to sort of flesh out the concept a little bit and give you a few of the major points in rocket science. You can all consider yourself rocket scientists when this is over. So the basic idea behind a rocket is that it propels itself forward by pushing on something that it has on board. This is in contrast to something like an airplane. An airplane propels itself forward by pushing on something outside of itself, namely the air around it. We'll come to airplanes later. Airplane pushes on the air, a swimmer pushes on the water. In those circumstances, there's no shortage of mass because stuff is always going by. You can always grab the stuff around you and throw it backward and give it backward momentum, and it consequently gives you forward momentum. In a rocket, mass is precious. You grab on mass that you have on board, and you throw it backward. And the act of throwing it backward, which involves pushing backward on it and giving it backward momentum, causes it to push you forward and give you forward momentum. Any questions about that basic idea? You take the deck chairs on your ship, throw them backward, and if you can give them 1,000 units of backward momentum, they'll give you 1,000 units of forward momentum. And off you go. Because mass is precious on a rocket ship, meaning that you can only throw it out once. It's gone forever once you've done it. You want to get the biggest bang you possibly can for your buck. You want to take the deck chair and you want to throw it backward as fast as you possibly can, because the momentum it carries away with it is proportional to its velocity. Double its velocity, and you double the momentum it carries in the backward direction, and consequently you get twice as much forward momentum out of it. So rockets, in propelling themselves forward, throw the stuff they have on board backward as fast as they possibly can. And giving that stuff very high speeds also means that in addition to carrying away a lot of backward momentum, the stuff carries away a lot of energy. Sad but true, it's sort of unavoidable. You throw back that stuff very fast, and it carries off a lot of kinetic energy. And you throw it twice as fast, it carries off 4 times as much energy, because remember, kinetic energy is proportional not to speed, but to speed squared. So very high speeds for that stuff going backward means that you had to give each kilogram of stuff a lot of energy. And that's why rockets, when at launch, they're packed full of extremely high energy stuff. Typically it's chemicals that are just the most wildly reactive things available. A lot of rockets basically are fueled by hydrogen and oxygen, which react in one of the most aggressive energy-releasing reactions there is. You can beat it, but not by much. So, lots of energy. Throw the stuff backward as fast as possible. And part of the throwing the stuff backward as fast as possible is it involves nozzles for directing the spray of gases. So this is just a little tidbit. The funny shape of the nozzles that you may have seen at the tails of rockets, actually even toy rockets, sky rockets and hobbyists' rockets have these nozzles of roughly the shape that I've drawn up here. It's called a de Laval nozzle after the scientist de Laval, or engineer, who invented it. And the basic idea, details don't matter. We're going to talk about gases very soon. In fact, later today I'll talk about gases in the context of balloons. But gases, what's between us right now, consists of countless tiny little particles. Some of them are atoms, but most of them are molecules, which are little assemblies of atoms. They are bouncing around like mad. Even at room temperature, they're bouncing around with thermal energy, which we'll come to. But if you make them hotter, they will have even more thermal energy. They're moving very fast, bouncing around, and if you can get that thermal motion to be directed in one direction rather than every which way, they'll go very fast. And so the de Laval nozzle, its whole purpose for being is to take the extremely hot gas produced by a ferocious chemical reaction, take those molecules which are going like crazy, and get them all get them organized so they all go backward like crazy, basically as fast as they possibly can. All their kinetic energy, which they call all their momentum's in the same direction. And what happens is inside the engine you have very high pressure gas, so it's hot and the pressure is enormous. We'll talk about pressure pretty soon, but you have some sense for pressure that when you open a bottle of soda and there's a lot of outward push. So you got high pressure gas in here. The gas then has a way out. It goes rushing towards the opening, and in the act of necking down to go into that opening, it speeds up. Its pressure drops. When we'll see how that works in about a week and a half. So the pressure, by the time it gets to the narrowest part of the nozzle, has dropped dramatically, and its speed, rather than being just bouncing around randomly, it's organized. It's going in one direction, essentially, well, primarily. And it's traveling so fast now that it's traveling at the speed of sound. What does that mean? Well, it's on the order of many hundreds of miles an hour. But it's traveling so fast at this point, when it's going through that area, that if someone were in it and were to clap their hands, okay, the ripple that is sound would actually not be able to make any progress backward, because the whole gas is going so fast that it's going fast as the sound itself would work its way through the gas. So it'd be like, hello, come and get me, come and get me, and the sound wouldn't make it back. So it's going as fast as the speed of sound. And beyond that, the nozzle necks out rather than getting narrower. And that actually helps to further direct the molecules. The whole point, so it goes from high pressure gas with no particular direction to very high speed, lower pressure gas with significant direction, to finally very low pressure gas traveling almost entirely directed. And very low pressure gas, just details here. Those nozzles are designed to operate to basically let the gas go out into the ambient surrounding gas. At atmospheric pressure, there's a lot of air here. You might not think of this stuff as anything significant, but it is. There's a lot of, there are a lot of molecules between my hands. Spraying a nozzle out into this is one thing. Spraying it out into empty space, quite different, because the gas goes out into nothing. It's a different experience for the gas, and the nozzles have to be tailored for their environment. So there are sea level nozzles, and then there are high atmosphere nozzles, and then finally there are nozzles suitable for empty space. And this is something that in the rocket engineers are paying attention to, the right nozzle for the right job, or even maybe nozzles that change shape somewhat so that they work properly over a range of places to operate. Bottom line, the nozzle's job is to take the hot, high-pressure gas, lots of energy, essentially no momentum yet, and redirect it so it carries a lot of momentum in one direction. It whisks the energy away with it too, but that's just a sorry side effect. Any questions about rocket nozzles? Not a lot to finally to remember permanently. It's just at least you might as well see it a little bit. Next question: how do you keep a rocket pointing forward? And for toy rockets or early rockets, the approach was one that involved aerodynamics, which is the science or engineering of of the flow of gases. And a rocket that you want the point of the rocket to fly forward. So this is an arrow, like you would get for target practice. There's the tip, there's the tail, and there are no feathers on it. And this guy is indifferent to which part of it flies forward. Why? Well, because the air doesn't affect it differently one place versus the other, and it just doesn't care which part's flying forward. But if you arrange it so the same kind of arrow with feathers on it, or fletching, as like an arrow that you actually would use, this one does care. It flies point first. And the reason for this is this guy is very stable. It's dynamically stable. The other one is not. This is apropos of bicycles. Remember, bicycles, when at rest, they have no particular stability. But in motion, the thing is stable. It spontaneously returns itself to a certain orientation. And so it's a little bit like balancing a broom with automatic steering. It automatically balances the broom. And how does this one work? Well, it's got a pivot, and actually it's supported, well, close to its natural pivot. The natural pivot is where? Right about. It's about an inch forward of the natural pivot. All right, but it's close enough. The air, however, when this is running around, the air exerts air resistance on it, and the air resistance on the front is relatively small because it doesn't expose much surface to the air, whereas the air resistance in the back is enormous. So when air is going by this, it exerts a force that tries to push the back further back. Slow down the back of the tail of the arrow. Don't let it come. Okay? So in effect, there is what's known as a center of aerodynamic pressure. Where along the overall arrow does the overall air force act? And it's back here somewhere near the feathers. The point then being is whenever the feathers get ahead of themselves, the air pushes back on the center of aerodynamic pressure and tries to get it to the rear of the flight. And it keeps pushing the tail of the arrow or the rocket toward the back. And so the back always flies, the tail flies at the back because the air keeps pushing back, that part back. Is that okay? Or questions about that at least? So this applies to an arrow. It applies to early airplanes, I guess. Is that true? Airplanes have that tail back there, the vertical stabilizer and the horizontal elevators. So they tend to push them to the back. Birds have a tail in the back. It would be pretty silly to have a bird flying sideways through the air. They like to fly nose first, more or less. So they use these sorts of tricks to get them to the back, to line up. If you recall, when I talked about bicycles and dynamic stability, things that self-correct, that love to keep going, orient themselves, or, for example, in the direction you want them, like an arrow, there's a trade-off. Having an arrow or a rocket or any of these, or airplane, that is very stable in motion, a lot of dynamic stability, it loves to reorient itself the way it's supposed to be going, that's great. It flies straight and true the way you want it, but you can't maneuver it very well. So an arrow like this has very little ability to maneuver. It can't steer. If you put a pilot in this arrow and they wanted to try to turn left or whatever, they'd have a tough time doing it. That too much tail. Same with airplanes. You want an airplane that's maneuverable, don't put too much tail on it. It's too hard to maneuver. So they shrink the tails, make it less dynamically stable. Now you got more control. I'm sure birds have evolved to have this. Some birds fly the same way all day, and they probably are nicely stable. And then there are other ones that want to be able to turn on a dime, and they're not so stable. All right? So simple rockets use the passing air to orient them. The days of simple rockets for anything beyond toy use is over. Modern rockets, instead of using dynamic stability like this, they go back to the basically unstable design, and they fix the problems using computers and the rocket engine itself. If you've got a rocket engine pushing, that is, it's throwing stuff out the back and having the stuff push it, it can use that rocket thrust, the push forward on the rocket. It can use it to adjust the orientation of the rocket if the rocket's pointing the wrong direction. And so modern rockets swivel their rocket the rocket nozzle. They change its direction subtly to obtain the forces and torques they need to point the way they want to go. So you don't see the big fins on the rockets anymore. They don't use them. First, that only works in the air where the air can push. They keep pushing the fins to the back. Once you get into empty space, there's nothing to push on anymore in terms of those fins. The fins are just decoration. And so there are lots of cases in the movies and stuff where you have these beautiful, streamlined, sleek fighter spacecraft, whatever, that never enter the atmosphere of a planet. But they fight like crazy out there in deep space. They don't need to be streamlined. A school bus is a perfectly good shape for a rocket in empty space because there's no passing air to push on it. Who cares? No air resistance problems. So modern rockets, they use their rocket thrust. I guess I should make sure I define rocket thrust right. Rocket thrust is the forward force exerted on the ship by the fuel and stuff that's thrown out the back. So you exert a million pounds of force on the gas, throwing it out the back. The gas pushes you, the rocket, forward with 1 million pounds of force. And that's sort of the kind of category, actually, some of these rockets have developed in the past. I don't know what the current rocket crop has in the way of forces, but they're huge forward forces, thrust forces. All right? Okay. How fast a rocket can go. So this gets back into sort of more central physics issues. Those previous things were more useful, hopefully useful knowledge. How fast can a spacecraft go? And the answer is there's really no limit, apart from the speed of light and stuff. That's a whole other story. And the issue is that to go faster and faster, the ship needs a lot of momentum. The momentum the ship has is its mass times its velocity. So if it's got a lot of mass, then probably its velocity is going to have some shortcomings. If it has less mass, well, then it can have more velocity. It's a trade-off between mass and velocity a little bit, given that you give it a certain momentum. So ships can go fastest when they have relatively little mass. It's just sort of simple math issue. In effect, you want the ship itself to have as little mass as you can get by with, because the story is going to be about exchanging momentum, and don't make the ship gobble too much of that momentum up by having too much mass. So that's part one. Part two is you want to have as much stuff on board as possible to throw out the tail. That is, you want a lot of fuel, because the more mass you can throw out the back, the more forward momentum you're going to be able to accumulate. So you want a lot of mass in the fuel, and you want to throw the fuel backward as fast as you possibly can. And that's an issue of the velocity of the fuel, sometimes called the exhaust velocity. You want a high exhaust velocity. So just to get down to basic issues, you want the ship to have relatively little mass, you want the fuel to have a lot of mass, and you want the fuel to go backward with as large a velocity as possible. All those lead to a high ship velocity in the opposite direction. So the simple-minded calculation of how fast the ship will go is as follows. First, assume that the ship and the fuel were together at rest. No movement, therefore no overall momentum. So you start with the ship and the fuel, all of them sitting still, no momentum. And now you redistribute the momentum in a funny way. You give the ship momentum one direction and the fuel momentum the other direction. In some, there's no momentum, there's still zero, but it's distributed funny. Two halves. Ship to the right, fuel to the left. Okay? The momentum the ship carries with it is its mass times its velocity. The momentum that the fuel carries with it is its mass times its velocity. And if you just solve that simple relationship, that the momentum of the ship is minus the momentum of the fuel, you end up with this equation. That the velocity of the ship, which has a minus sign, is equal to minus, as in it's in the direction opposite, the mass of the fuel divided by the mass of the ship times the velocity of the fuel. This is not a complicated equation to figure out yourself, I hope. What this is just telling us is, you want a big ship velocity, you want as much mass in the fuel as possible, as little mass in the ship as possible, and the biggest possible velocity for the fuel itself. So this is the simplistic version of the rocket, what's called the rocket equation. Basically, you throw all the fuel out at the full-blown exhaust velocity, bang, you throw it in one fell swoop, and the ship then will go forward at that velocity. It's just equating their two momenta apart from a change in direction. Is that okay? Yeah. Okay. Why is it negative? It's because the velocity of the ship is in the opposite direction of the velocity of the fuel. This relationship is actually a relationship between vectors, which have direction to it. Velocity of the ship might be to your right, velocity of the fuel is to your left, which is minus velocity to the right. That's the minus sign. It's the reversal direction. Is that okay? So, I mean, a first observation you can make out of this is all the big time rockets. First off, at launch, they are enormous fraction of the rocket itself is fuel. They are big bottles of fuel and not much else. And that's why when they have a disaster, it's a crazy wild disaster. They're 80%, 70 or 80 or 90% fuel, as much fuel as they can get without. It's hard to get beyond a certain fraction of fuel because containing the damn stuff is hard. These are wildly reactive, often very cold chemicals, liquid oxygen and stuff. So containing it without having it leak and stuff is difficult. But they try to get basically as hollow a shell that weighs almost nothing around this bottle of fuel. Get the fuel mass way up and the ship mass way down. And they also try to have the fuel go out as exhaust as fast as possible. And the modern rockets send their fuel out at miles per second, 3, 5 miles per second. Those plumes of gas that are coming out of there are traveling from here to Crozet in 1 second. Like crazy. All right. One other observation is all the rockets that ultimately get to orbit, in order to get the fuel ratio, the amount of fuel up high enough relative to the spacecraft, they have to keep throwing away parts of the spacecraft. They have to throw away the empty bottles, basically. And so spacecraft are staged. Back in my youth, they were literally staged. Like the Saturn V rockets that went up, that took the Apollo missions to the moon, they were a stack of rocket upon a rocket upon a rocket. So they'd launch the big rocket, it would go up some distance, and then they would have used all the fuel in the biggest bottle. They would then throw the bottle away. It was, releasing stage 1. So they would get rid of the whole rocket. Then they would turn on the second stage, which was essentially a little rocket on top of the big first rocket. And then that would go. And when that fuel bottles were empty, they would throw that one away and go to the last stage, perhaps. So the staging technique was very visible way back in the 60s and 70s. It's more subtle now, but it's still there. So the rockets that launch these days, they're still throwing away the early bottles. And I guess some of the big whoop-de-doo right now is trying to get that bottle to come back and land so they can use it again. So the initial, the starting rocket, they want to be able to reuse those instead of destroying them or whatever. So that's this simplistic equation. It's a little simplistic for the following reason, and that is rockets don't take all the fuel and throw it out in one instant. Bang, throw it out, all of it going full speed, and therefore and reacting as a result. They throw the fuel out a little at a time, and they begin to move as they throw the fuel out. And therefore, the fuel isn't coming out of a motionless rocket. It's coming out of a rocket that is gradually going faster and faster in the direction the rocket wants to go. And as a consequence, the fuel that's thrown out late in this story has already was caused to move forward. It's already moving that way. And when they throw it out, even as hard and fast as they can, it doesn't end up traveling at the full speed of the exhaust when the rocket was motionless. It's coming out of a moving object. And think of it as you're passenger in a car. I won't have you drive it. And you're going to be throwing tennis balls out. And the first tennis ball you throw out backwards. The car's parked. You throw it backwards, and you've got a good arm, and you're throwing it 70 miles an hour backwards. But now the car starts heading forward. And it's at 30 miles an hour. You throw it out, you're still throwing it 70 miles an hour as far as you're concerned, but to a passerby, because you were moving forward, it's coming out of a moving car, it's going backward not at 70 miles an hour for the passerby standing there, but rather only 40 miles an hour. You have to take into account that it came from a moving car. And by the time you get up to 70 miles an hour and you're throwing the ball backwards at 70 miles an hour, the ball just is motionless as viewed by the passersby. They just see a fast-moving car going by with a person tossing the ball out that just stops and falls. Can you visualize that? The consequence of this is a rocket doesn't get quite as much momentum out of its fuel as it would from the simplistic relationship, this one on top. Because the fuel is being thrown out of a rapidly accelerating object, one that's going faster and faster, and therefore making worse and worse use of its fuel as it's coming out of a very fast-moving rocket. The fuel may not even go backward at all. It may actually be going a little bit forward. The real equation for how fast the ship can go is still proportional to the velocity of the exhaust velocity, and it still has to do with the mass of the fuel and the mass of the ship, but it's got a logarithm in it, natural logarithms. I don't know whether you're familiar with. Hopefully, you're familiar with a logarithm. It's the inverse function of an exponential, and the details aren't so important. But this ship velocity is always less, and significantly so, than the velocity it would have if it sent all its fuel out backward in one instant, kind of like a cannon. You never get the speed you want. However, it is still possible to get this velocity to go larger and larger. There's no limit to how fast the ship can go, but it requires a greater and greater fuel fraction. So if you're willing to have a ship that at launch was 99.9999999% fuel, you can make the ship go really, really fast, but it's very hard to make a ship like that. So, anything else worth talking about here? Yeah, one interesting thing is the ship can go faster than the exhaust velocity of fuel. So if you can send the fuel out at 5 miles an hour, 5 miles a second, you might think the ship can't go any faster than 5 miles a second, but it can, and it does. The spacecraft that go into Earth orbit end up having to go 17 miles. Is it 17 miles per second? I can't remember it. I forget the numbers. It's really, really fast. That doesn't help much. It's faster than the exhaust velocity of the engines. So they do get there. 17,000. dang, 70,000 miles per hour, which is divided by 3, it's 5, 6, 7 miles per second. It's pretty fast. It's faster than the exhaust velocities typically. All right? So, yeah. So, you launch a rocket. So it's just, I'm just thinking the theme here. You launch a rocket, it starts throwing fuel down as exhaust, taking downward momentum with it. It gets upward momentum. It begins to accumulate that upward momentum, goes faster and faster. Gravity does play a role, and gravity naturally makes it harder to launch a rocket upward. But finally, it's not a crucial player in the launch process. The forces are so enormous that they still manage to take these ships off without too much trouble and cause them to accelerate to tremendous speeds. As I'll talk about shortly, rockets that are headed for orbit or for basically for space don't go straight up. They go sideways to a very, very large extent. And we'll talk about that shortly. But what I do want to point out is that once the ship gets above the Earth's atmosphere, and we'll talk about what an orbit looks like in a second, there's, in popular press or something like that, it's the idea that suddenly they no longer have any weight. Just because they got out of the air and into the space above, the empty space above the Earth, it's as though, well, the weight went away. The answer to that observation or the response is that no, they still have weight. The astronauts, since apart from the ones that went off to the moon in the 70s, in the 60s and 70s, the astronauts have all been near the Earth's surface, within a few hundred miles of the Earth's surface. Consequently, they have had nearly their full Earth weight, Earth's surface weight, throughout their time aloft. They never became truly weightless. They just had slightly lighter than normal weights. And to understand why, we can look at what's known as the universal law of universal gravitation. When I first introduced the idea of falling, an object falling here to the Earth's surface, I kept having to say near the Earth's surface and stuff like that, because gravity does get weaker with distance. And the only object that's with enough mass that's near enough to us to exert a significant gravity on us is this globe we call the Earth. And the force it exerts on us is proportional to the Earth's mass, our mass, and the distance separating the two of us. And you might say, well, the distance separating us from the Earth is a couple feet. Well, no, it's actually, you have to take into account all the Earth's mass, not just the part that's right beneath your feet. When you do that, when you sum over all the pieces of the Earth, it turns out that the location, the effective location of the Earth's mass in terms of exerting gravity on you is the center of the Earth. It's center of mass. So your weight, how hard the Earth pulls on you with gravity, is equal to, well, there's a constant that relates what I'm about to say to your weight, and that constant has a name. It's called the gravitational constant. But it's the mass of you if you're the ship, and this is specialized for a ship. But your weight is your mass times the Earth's mass divided by how far apart those two masses are. Your mass is your center of mass, effectively, and the Earth's mass is its center of mass, effectively, which is about 400 miles from here, down there. So the distance is about 4,000 miles. I hope I said 4,000. 4,000 miles. And that distance actually shows up in this relationship squared. So 4,000 miles squared. And this constant is a very small constant. But anyway, because the mass of the Earth is so huge. So your weight is this gravitational constant times the mass of you, the mass of the Earth, divided by this 4,000 mile distance separating us squared. Is that okay? This relationship works for any two objects, not just Earth and you. It works for two of you. you and you are exerting gravitational forces on each other that are proportional to your mass times your mass divided by the distance separating you, a couple feet, tens of feet, squared. Those forces are very small because your masses aren't big enough. The product of your masses is tiny compared to the product of your mass times the Earth's mass. But in a laboratory, you can measure this. It's actually possible to measure the gravitational force basically between a bowling ball and another bowling ball when they're close. And people have done that, and that's one of the ways in which they've determined how strong this gravitational constant is. Any questions about this idea of law of universal gravitation? In the long run, it turns out to be an approximation to what's known as the general theory of relativity, which is another way of looking at gravity. But this is very good. It's a very good approximation for all practical purposes. And having come up with this, if you now go back to the mass of a ship that's orbiting the Earth, that's 100 miles above the Earth's surface, well, the distance separating the center of the ship and the center of the Earth is bigger than it would be if the ship were on Earth, but not much. Instead of being 4,000 miles, as it would be if the ship were on the ground, it's 4,100 miles. And you take that and square it. It's 5% difference. The ship experiences a little bit less weight, but only 5% less. So where this all goes is that the astronauts in orbit pretty much weigh their full Earth weight minus a little bit. Is that okay? So then you think like, okay. So if they weigh like crazy already, they still weigh 100 pounds, 200 pounds, why aren't they falling? Is that okay? They are falling. So when the rocket engine turns off and just leaves the astronaut and or the ship, whatever, free of all forces except the Earth's gravity, the Earth's gravity is still there. It's still pretty nearly as strong as it would be on the ground. They're falling objects. They're falling like crazy. It's not 9.8 meters per second squared. It's 9.7 or something like that, or 9.6. Big deal. It just delays the inevitable. Smack, right? So how do they not smack? And the answer to that is they're heading sideways like crazy. So here are the two possibilities. The spaceship or you or something like that, out there, released from rest, motionless. What happens? You accelerate downward because you have a weight. It's a little bit less than normal, so you don't accelerate quite as fast. But you start picking up downward velocity. You go faster and faster. And as you get closer, your weight increases a little bit. Your acceleration increases a little bit. And so you're picking up speed, and you're actually picking up speed at an increasing rate. And you go faster and faster, and splat. Big disaster. That doesn't happen. And the reason it doesn't happen is because at no time are the astronauts motionless. After the rocket engine turns off, they are not motionless at all. They're heading horizontally at a tremendous speed, like 17,000 miles per hour is the number that comes to mind. And these things I used to know as a kid, like I memorized them all, and they've gotten fuzzier in my head since. But it's about, I think that's the right number, 17,000 miles per hour is how fast any of these low Earth orbiting spacecraft are traveling sideways. And the advantage of traveling sideways that fast is that although they do have weight and they are accelerating downward at pretty nearly 9.8 meters per second squared, that is curving their path, not dictating it. They're like on a carousel. So there's the center of the Earth right here. And I'll be the spacecraft, and I'm accelerating towards the center, but because I'm going sideways very fast, it's like a carousel is turning rapidly. My path is bending, but I'm not getting any closer to the center, even though I'm accelerating toward the center. An orbiting spacecraft is pulled toward the center of the Earth by gravity, by its weight. It accelerates toward the center of the Earth, and its velocity changes in direction, but its speed doesn't increase or decrease. This is in a perfectly circular orbit. In a perfectly circular orbit, the speed stays constant, and the acceleration is always exactly at right angles to the velocity, always toward the center, and around it goes. Any questions about that idea? That a spacecraft going fast enough sideways never descends. Another way to think about this is that the spacecraft's inertia wants it to go straight and leave the Earth, and therefore go to higher and higher altitude, essentially ultimately to infinity. So inertia wants an increasing altitude. Gravity is pulling down. It wants a decreasing altitude. Its tendency is to decrease the altitude of whatever stuff is up there. And if you balance those right, the inertial tendency to go straight and go to higher altitude, with the gravitational tendency to go down to lower altitude, if you get it just right, you make progress in either way. And so that's what's happening with the astronauts and their ships and all of the stuff. They're chronically, they're staying at the same altitude the whole time, more or less. Yeah. Okay. Yeah, well, yeah, how perfectly do you have to get it matched? To maintain a circular orbit, you've got to be right spot on. But if you are a little slow, if you're traveling a little slow, what happens is gravity begins to win. You begin to make progress toward the Earth a little bit, but you speed up in the process because you're converting gravitational potential energy into kinetic energy. You speed up, and that compensates, and then you whip around, you still orbit, and you come back. You're in an elliptical orbit now, and the point where we started the story is, in principle, is your highest, farthest from the Earth, your apogee. If you're going a little too fast, now you begin to make progress away from the Earth, and you slow down because you're turning kinetic energy to gravitational, and you go into another elliptical orbit. And where we started is now you're closest to the Earth. It's your perigee. You got a pretty large window. The window has two limits. If you go too slow, then you'll follow an elliptical orbit, but it may take you into the Earth's atmosphere, and that's the end of things. And that is how, when the astronauts want to come back, that's what they do. They slow down. They deliberately slow the ship a little bit. And now the balance, they spoil the balance between inertial and gravitational, and they make progress toward the Earth, and they just carefully, very strategically come into the Earth's atmosphere, which really slows them down, and they land. So that's the landing process. On the other hand, suppose you're in orbit and you want to leave the Earth's orbit and go off, say, to the moon. What do? You speed up. And you speed up. If you speed up a little, you'll go into an elliptical orbit that still closes on itself and is a loop, but it's a big loop that's not quite circular anymore. You guys have dealt with ellipses. They're oval shapes stuff. They have a mathematical definition that they truly are ellipses. And you can make that ellipse bigger and bigger. The faster you go, the harder you make it for gravity to bend your path back in, the bigger the ellipse comes. And there actually is a limit beyond which, if you just go into that limit, the ellipse never quite closes. And that shape isn't an ellipse anymore. It's known as a parabola. It closes sort of at infinity. And if you go even faster, you go into the next kind of curve, which is known as a hyperbola. A parabola is a special case of a hyperbola. So those curves, but they're all very closely related curves. They're all related. They're what are known as conic sections. They're all related to slices with a samurai slice through a cone. You can cut out all these shapes. A circle is just, here's the cone, right across the top. An ellipse at an angle. A parabola, perfect slice, parallel to one of the faces of the cone. And a hyperbola is just like, let's go straight down. So they're all there. The point of this is that the astronauts are working with these orbital shapes to do what they want to do. They want to go from low Earth orbit to high Earth orbit, farther away. They start in the low Earth orbit. They speed up. They get themselves into an elliptical orbit. And when they're out there at the distance they like, they speed up again and shift into a circle that stays circular. If they want to leave the Earth to go, say, to the moon, they speed up even more. They go into a parabolic or hyperbolic orbit temporarily, and they have one that's aimed at the moon. When they go past the moon and they want to go into moon orbit, they slow down and get go into a circular or elliptical orbit around the moon. So this is all the games they played. If you watch the movie Apollo 13, you can see that they had already gone into the one taking them toward the moon. They had to go around the moon. I think they never remained at the moon. I think they orbited partly once and came right back. Yeah. Yep. Yeah. Yeah. Yes. 17,000 miles an hour is the right speed for a circular orbit at just above the Earth's atmosphere, 70,000 miles an hour. It creates an orbit that takes, is it 84, 90, it's not, I think that's 90-minute orbit. They've got no control over this. It has to be 90 minutes because the speed dictates and the distance gives you 90 minutes, right? At the Earth's surface, I think the orbit is 84 minutes. Air is in the way, which is kind of a nuisance. So if you got rid of all the air and you fired a gun sideways at that about 70,000 miles an hour, the bullet would be going so fast that although it would fall, it's a falling object. As it fell, one way to think about it is it's falling, but the Earth is curving. And the fall and the curve are perfectly synchronized. It never makes any progress. It would come around and actually, in principle, it would come and get you. So you'd have 84 minutes to write your last will and testament. And then, whew, doc, it would keep on going. And this is Newton, I think I put it in the book. Newton drew this whole idea of what if you took a cannon on the top of a mountain and fired it sideways, and if you fire it slowly, of course, it goes thunk, thunk. You fire it a little faster, thunk, thunk, and then as you get really fast, it begins to circle. And I animated this on the book, so that same idea that it finally goes into this orbit. All right, so I managed not to get to balloons at all. That's the story of rockets pretty well, I think. And we'll continue with balloons on Wednesday. Enjoy the break.